And then some Francisco Santos Leal from the University of Cantabria in May 2010 announced a counterexample, and the paper presented a 43-dimensional polytope of 86 facets with a diameter more than 43. The counterexample has no direct consequences for the analysis of the simplex method, as it does not rule out the possibility of a larger but linear or polynomial number of steps. Sorry, I'm intruding into your lecture now.
No, nobody's come, so it's okay. Shubhada is there. So let me just check if this live streaming is working. I've just gone on live streaming. So okay, there seems to be something happening, so it's okay. So good morning. Maybe we should start. I'll wait for a minute and then we can start. Are you able to hear me okay? This room is a little noisy.
Yeah, we can hear you.
Okay. So, all right. So we've been talking about linear programs, and our plan today is to somehow prepare things for introducing the simplex method next time. So I'll be following the book closely, and the idea is to work with the equational form of a linear program. Okay, so I'll tell you what an equational form is, and then how any linear program can be transformed to the equational form. Then we'll study some small geometric properties of the equational form related to notions that you usually associate with convex polyhedra and polytopes, like vertices and things like that. So let's start. So we've been talking about linear programs, and maybe we realized that all linear programs can somehow be written in this form with a few multiplications with -1 and transforming equalities into two inequalities. Yeah. So this, let us call this the general form of a linear program. Okay. Now, when we do simplex method and when we try to analyze algorithms for linear program using the simplex method, we will use what's called the equational form of the linear program. So what happens in the equational form? In the equational form, the objective function still stays the same, yeah, C transpose X. the difference is in the constraints. All our constraints, or most of the constraints where this matrix is involved, have to be in equality form. The only inequalities appear here. Okay. It's very strange. Yeah. So it is like a system of linear equations, and then the only inequalities are that all the variables should be non-negative. So the non-negativity constraints are the only inequalities that we have. All the rest has to be equality. Okay. So it looks like a restrictive form of linear programs. And it turns out that with a little bit of manipulation, any general linear program like this can be transformed to equational form. Okay. We might have to add some additional variables. So some of you are probably quite aware of these standard tricks used to transform linear programs into equational forms, but I will just go over them one by one. Okay. So the first thing is that in the general form, there are these inequalities. A typical inequality, for example, looks like this. Okay, and we don't want this inequality. We would like to convert it to an equality. So what we do is, instead of saying that 2x1 minus x2 is less than 4, we say 2x1 minus x2 plus a variable z, z1, is equal to 4. So this z1 contains the gap or the slack between the right-hand side and the left-hand side. And to properly capture this inequality, we have to say that z1 must be greater than or equal to 0. And similarly, when you have inequality in the other direction, this we dealt with last time itself. We could, for example, multiply both sides by -1, change the sign to less than equal to, and then apply this principle. Or you could say that the slack is negative, but you explicitly write the minus sign here. So you say that this quantity subtracted, reduced by some z2 must be equal to 4, and again you set z2 greater than or equal to 0. So either way, yeah, you can you see that we introduce these slack variables in order to convert inequalities to equalities. So this is one transformation that we need to do in order to get the linear program into equational form. The other thing is that here, the important thing is that every variable is set to be non-negative. Now, in a general linear program, there might be variables which are not constrained in any way. Okay, I mean, a linear program is free to say that some variables can take both positive and negative values. So we would nevertheless like to have constrained variables in the equational form. Every variable must be restricted to the positive side, non-negative side. Okay, so what we do, and this is a trick we saw last time in dealing with absolute values. So basically, we had this variable xi in our original linear program, and what we do is we introduce two new variables, and they will be set to be greater than 0, but xi will be set to be the difference between yi and zi. Okay, so one possibility is that so we will systematically go through all the so which one? Yeah, so suppose we have managed to put it in equational form, but some variables are still left unconstrained. Okay, so for each of those variables xi, replace the occurrence of xi by yi minus zi in that equation. So xi is out. Yeah, and similarly, if xi appears in the objective function, you again replace that xi by yi minus zi, open the brackets so that it looks nice. Yeah. And now the yi and zi, you impose the non-negativity constraint. Okay. And now you had the old linear program where xi was unconstrained. You have a new linear program in equational form where that xi has been replaced by yi and zi, and yi and zi have been set to be greater than 0. Okay. Now we will, I'm not going to do this carefully this time, that we need to show that the two linear programs have the same, there is a correspondence between their solutions. And the point is that if you had an xi, and if xi is positive, then you can probably set yi to be equal to xi and set zi to 0. And on the other hand, if xi was taking a negative value in your optimal solution, you could construct a solution for this new linear program with zi set to the absolute value of xi and yi set to 0. So that will show that the new optimal new linear program is not worse, is achieving a maximum which is at least what was being achieved before, and you can go backwards. So if you're given a yi and zi, you can somehow set one of them to be 0. We can assume one of them is 0 and go back and produce the xi for the other linear program, the original linear program. Okay. So that's all I wanted to say about transforming any arbitrary linear program into equational form. Are there any questions? So what happens? So I would like to talk a little bit about the geometry of what is happening when we put these linear programs in equational form. So let us focus only on the equations. Yeah? So there is a part of the linear program which looks like ax equals b. So each equation here yields a hyperplane like this. Okay, and in the end, all those equations must hold. That means we are looking at those points which are in the intersection of these hyperplanes. By a hyperplane, I just mean a1x1 plus a2x2 plus anxn equals some scalar value b. Yeah. So it's an equation of a plane, but doesn't necessarily need to pass through the origin. It can be shifted. So it's an affine plane. Yeah. And then you have many affine planes, and we are in some high dimensional space. So after they cut off each other, we are left with a region like this, which is an affine space of some perhaps smaller dimension. And that is what these equations leave us with. We are trying to optimize things within this. Okay. So then we have this positive non-negativity constraint. So we work with the positive orthant, or you can say the non-negative orthant. So for example, if we were in 3 dimensions and these were the 3 axes, and suppose you had one equation which said that the point feasible region must be a subset of this plane. Now, when you intersect the positive orthant with this plane, you are left with this, this sort of triangular region. That becomes your feasible region. So in general, when you have many equations, in the end, you'll be left with an affine space, and that affine space will pass through the positive orthant. Everything outside the positive orthant is clipped out, and only the part that remains within the positive orthant is your feasible region. And when you try to optimize, you are trying to find a point where the optimum, where the objective function takes the maximum value, but confined to the positive non-negative orthant. Yeah. Is this clear? It's a very simple picture in 3 dimensions, and So you will try to find. So there will be an objective function defined by the vector c, and you're trying to find out which point in this region gives you the best value, best dot product with that C. So before, when we do simplex method, there is some initial cleanup that we can do so that things are nice. So there are two things I would like to talk about. One is that we will assume that this system, yeah. So you see, there was this intersection of hyperplanes, and it could be that these hyperplanes have no point in their intersection, in which case the equational linear program is actually infeasible. There is no feasible point, because these equality constraints are somehow mutually contradictory. Now, so what we will do is, so when we are thinking about it algorithmically, we will first look at this system of equations and use Gaussian elimination, yeah, or some other method to find out if this system has a solution at all. Yeah, it need not be a feasible solution of our linear program. Okay, yeah, these non-negativity constraints need not be satisfied. First, we are asking, just as a system of equations, does it have a solution? Okay. And we determine whether it has at least one solution. If it does not have any solution, we just declare the linear program to be infeasible and we are done. Okay, so this is one sort of ad hoc initial Gaussian elimination step that we perform, Gaussian elimination algorithm that we perform to determine if this system has a solution. The second thing is, we will assume that the rows of the matrix are linearly independent. Yeah. So when you have the thing in equational form like this, yeah, so we will assume that the various rows are linearly independent, because if they were linearly dependent, and if the system was, if this system had a solution, then it must be that one of the equations is a linear combination of the other equations. Okay, in which case any solution that satisfies, or any point that satisfies the other equations, will automatically satisfy this equation. Okay, so we can eliminate these equations. So one by one, yeah. So this is also something Gaussian elimination will help you do. Yeah. So you just look at this and you put it in row echelon form and throw away all those equations at the end, which will be of the form 0 equals 0 or something like that. Okay. So yeah, so we might as well assume that this A has already been, or this system, we have done the initial row echelon form algorithm on this. So we can assume that all the equations that we have are linearly independent, or the rows of A are linearly independent. Any questions? Yeah. So from now on, we will use these two parameters, M and N. So M will be the number of rows in this matrix A, and N will be the number of variables that we have. Okay. And we will assume that the rows of this matrix are linearly independent. So I want to now talk about a very important notion called basic feasible solutions. We'll be focusing only on linear programs which are in equational form, and we'll be looking at basic feasible solutions. So what's a basic feasible solution? Okay, so I'll tell you very soon, but just the geometric picture that you should have is that, you know, this point P is not a basic feasible solution. This point Q is not a basic feasible solution. These are feasible solutions, but they are not basic feasible. But somehow this point R is a basic feasible solution. And why that will happen, why that is true, depends on the definition of basic feasible that we are going to present soon. But suppose, in addition to this plane, we also had this one more equation. Okay, so I don't know if you're seeing the same picture that I tried to draw. That is, you had this and you are going to slice it with another plane which comes across like this plane. Then what it will select out this little line segment here. Okay, so the very same point Q perhaps, which was earlier not a basic feasible solution, might become a basic feasible solution. Okay, so it depends on what affine space you were left with by the equations, and then when you intersect that affine space with the non-negative orthant, some points arise which are called basic feasible solution. So this is the geometric picture. The connection between them and the algebraic definition that I'm going to present now may not immediately be clear, but I will not be trying to describe the exact correspondence because it's not even clear what we mean when we point to things in the picture. Okay, so we will have an algebraic definition of what is a basic feasible solution, and then we will proceed from there. Okay, so so we need to take our time over this. So suppose you have a matrix. So this is the matrix A, and you have a subset B of the columns. So N is the indices for the columns, and B is a subset of the columns. Now, by A sub B, we mean you restrict A only to the columns in this set B. B is a set of columns. You just throw away the other columns, retain only the columns in B.
This would be consisting of those rows of those columns of A whose indices appear in B. Right?
Sorry, so what did I write?
You wrote consisting of those rows of A whose indices appear.
Yeah, this is wrong. Yeah, I'm sorry. Let me just correct that. How do I do this? So yes, A sub B is those columns of A. Thank you. Yeah. Columns of A whose indices appear in B. Okay. So what's a basic feasible solution? So look at a feasible solution of this linear program, which is in equational form. Yeah, this linear program. And look at those places where, so we are looking at a particular feasible solution, and look at those values of X. Yeah, so let me maybe try to draw. So here was your feasible solution. Yeah. So there was some value alpha 1, alpha 2, alpha n. Now some of them were 0 and some of them were non-zero. So suppose these were strictly greater than 0, because variables, if they are non-zero, they have to be greater than 0. So look at those positions, those indices where the variables are greater than 0. Now let's assume that there are m of them. Yeah. Then if you look at those columns of A, those m columns of A, they should form, those columns should be linearly independent. Okay, so let me just read out what is written. What I said might have been confusing. Okay, so you've been given a matrix A. Yeah, this matrix A. Look at some columns, some m columns, which are linearly independent. Okay, and just restrict yourself to that square matrix and solve the equation. That is, the remaining variables outside B you set to 0 and you solve them. And if you happen to get a solution which is feasible, then it will be called a basic feasible solution. So it is a feasible solution which was obtained by solving a system of m equations where you had only m columns. Yeah, a system of m equations where the matrix that you solved was a square matrix. Okay, so you had this. Maybe I'll just. So you had this.
Then just to be sure, if n is less than m, then there is no such solution.
Sorry? No,
If
so
n
we
is
assume that the rows of A are linearly independent. So
okay.
the number of rows can be at most n.
At most n.
Yeah, so there is scope for doing the right thing here. Yeah, so n will always be at least n in our setup, because we are in equational form with the assumption that the rows are linearly independent. Now you take any matrix B, not necessarily of contiguous columns here, and set the other variables corresponding to the other positions to be 0, and solve this system of equation. If it turns out that all your variables came out to be non-negative, they can be 0, of course, and the other variables anyway you have set to 0, then this particular solution will be called a basic feasible solution. So instead of solving the linear program, you just solve a system of equations to obtain this solution. So here is some facts which you know from linear algebra, that suppose this particular matrix, so you took some columns B, and it turned out that this matrix is non-singular, that is, the columns are linearly independent. Okay. Then there exists at most one feasible solution which is supported on B. That is, all the non-zero entries of the solution appear on B. And the reason is that you can throw away the other columns, restrict yourself to just the columns in B. So you're solving an equation which looks like B x sub B equals D. So you have set the variables outside of B to be 0, and you're trying to solve this equation. Now, if the columns of B are linearly independent, then you can have at most one solution. You can have at most one solution, because if you had two solutions, then their difference would be in the null space of B. But if the columns of B are linearly independent, the null space of B consists of only the 0 vector. Okay. The only dependency among the columns of B will be the 0 dependency, or there is no dependency. So, which means that for each potential B, there is only at most one basic feasible solution that is supported on B. Now, two different Bs can give rise to the same basic feasible solution. And that is because when you try to solve the system for B, it may be that in addition to the variables outside B, some variables inside B also came out to be 0. That means now if you consider some other B which has these columns in common, and if you try to solve the system for the other B, you will get the same solution. This is because of some funny situation with zeros appearing in the solution. Okay. But that's not the point. If you're given a particular B which is non-singular, then either you have no basic feasible solution corresponding to B, or if there is one, there can be only one. Okay, there cannot be many. Okay, so which in particular says that there are only finitely many basic feasible solutions. Okay, so which is a very pleasant thing. I mean, in general, when you have a linear program, it's a infinite space. There are things which are inside which we know we should be eliminating because the optimum cannot happen inside, which is our geometric intuition. But furthermore, even on the surface of the space that we are trying to, which is our feasible space, there are some special points which are called basic feasible solutions. And what we will show next is that the optimum always happens at one of these basic feasible solutions. So let me say it correctly. We can restrict attention to just basic feasible solutions, and we will not miss the optimum solution. So there will, so let me just say it and read out what is written. So if the objective function of an LP is bounded above, we are looking at maximization LPs. If the objective function of an LP is bounded above, then for every feasible solution, so you give me any feasible solution, there is a basic feasible solution which does as well. Okay, so this is the objective function returned by a basic feasible solution. Yeah. So depending on the solution you have given me, I can construct a basic feasible solution which will do at least as well. Yeah. So which means that when you have a system in equational form, you can restrict attention to basic feasible solutions when you are searching for the optimum solution. Is the theorem clear? We'll come to its proof. If there are any questions about what I'm saying. Yeah. So you see, okay, so I would like you to keep this picture in mind, this one, yeah, this one. Okay. So you had the non-negative orthant, and then you had an affine space which cut through the non-negative orthant. Now, of course, I had always been drawing misleading pictures where when you cut the space, you got some sort of a bounded figure. But the figure need not be bounded. The slice that you took of the non-negative orthant might open up into the positive side, yeah, which is more like what is here. Okay. So just to be careful, I've drawn this in this way, which keeps it slightly more general. Okay. So now let us see how we are going to prove this. Okay. So somebody has given us a solution x0, whether it's optimum or not, we don't need. We have given a solution. Now we ask which are the positions where this solution has positive values. Okay, so which are the columns where this feasible solution has positive values? Now, if those columns are linearly independent, yeah, then we are done. Because what we will do is, if there are already m of them, then x0 itself is a basic feasible solution. If there are not m of them, then there must be fewer than m, because the number of rows is only m. So we cannot have more than m linearly independent columns. So maybe there are maybe m-1 columns where x0 has positive values. Okay. Now we know that the column space has rank m. Okay, and you have learned in your linear algebra course that whenever you have a linearly independent set, yeah, with m vectors and of m-1 vectors in a space of dimension m, then you can always add a vector from outside into this so that this new thing also stays linearly independent. So you might have had, so look at the positions where x0 has positive values. If those columns are linearly independent, then you can just perhaps augment it with more columns so that it becomes full rank, and then you will be left with a square matrix. And for that square matrix, with respect to that square matrix, which we can now call B, x0 itself will be a basic feasible solution. But that's a very kind of happy and lucky situation where the initial initial feasible solution that you have been given already turns out somehow to be basic. Yeah. But suppose that was not the case. That is, the columns that you had, yeah, we don't know how many of them, but they happen to be linearly dependent. That means if we restrict ourselves to that matrix, yeah, matrix corresponding to the columns where x0 has a positive value, this is a singular matrix. That means there is some dependency between the columns. So there is a vector W, so that this matrix A times this W. So this W has non-zero values only in these, in the columns corresponding to K. And this A times W is, so now I would like to go back to the picture and imagine what this W is. So this is our W. Yeah. And look at this W, it is some vector. This was your original solution. Now, if you move on this line, yeah, in either direction with respect to W, these equations will still be satisfied because you have added W to X naught or a constant factor times W. Yeah, you have added some constant factor times W to X naught. Since the W part doesn't change the left-hand side, the system will continue to be satisfied. Okay. The point is that W is non-zero. So as we move, at least in one of the directions, we will at some point violate some non-negativity constraint. Okay, so that's why it was important. There were these non-negativity constraints, and it may be that if you moved in the direction W, all those non-negativity constraints were already satisfied, and W has only positive values for everybody. Okay, if all the entries in W were sort of positive or non-negative, then you can move in this direction indefinitely. Yeah, not in my picture, but yes, in general, if yes, some direction like this, you could move in that direction indefinitely and never get any violation. Okay, that's not what we are going to do. If that is the case, then we move in the opposite direction. Yeah? If we move in the opposite direction, some variable must be reducing in value, and there will come a time when we hit the wall. That is, we can't go any further, and we still will be left with a solution. And what is better about this solution compared to the previous one? One more variable has been set to 0. Okay, so X naught had a certain number of variables which were set to 0, which were 0, and now by moving in the direction W, we will have reached a point where one more variable has been set to 0. Okay, so we start now. We call this solution X1 a new feasible solution, and ask whether it is basic feasible by using the same process. And then if it is not, there is some direction in which we can move, and in moving in one of the directions, for example, in this, if we moved in this direction, we will keep staying feasible. There is no problem. But if we moved in the opposite direction, sorry, where did I go? Yeah, we will have reached this point. Okay, maybe we will call this X2 and so on. Okay. Now you're keeping on dropping columns. So at some point you'll be left with only sort of one column. Yeah, and then you'll know that you have basic feasible. You can then extend that to a basis, and you'll get a basic feasible solution. So all this can be said very compactly. So I should probably have said, given X naught, consider that basic feasible, that solution, that feasible solution, which has the largest number of zeros. Okay, and then in one step you get a contradiction. But we did it sort of slightly algorithmically, because there are many situations where this argument is made. That is, if you have a solution which is somehow embedded inside a convex space, you can move to the boundary along a line, and this will come up often in applications of such ideas. So I just wanted to give you some sort of an algorithmic flavor of what is happening. So yeah,
can we repeat this thing when the number of independent number of columns were greater than m in number of so X naught was initial feasible solution and its non-zero entries were greater than m. Can we once again go over this argument? Actually?
Yeah. So it need not have been greater than m. It could be even less than m, but they just happen to be dependent.
Yeah.
So both cases are there, but let me just first say yours. So maybe I will draw somewhere and write. Okay, yeah. So here was X naught, and X naught. Let me just say that the first m plus 1 of these entries were positive, and these were 0. Okay, and now here is this matrix, and you have the first m plus 1 columns here, but the total number of columns is only n. Total number of rows is only n. Okay, and you have m plus 1 columns. This is the set K that I'm talking about here. Okay, these indices are the set K. Now, these cannot be independent because we are in a space of dimension only m. So there is a dependency among them, and that dependency, which has only one non-zeros here and zeros there. Yeah, so that dependency I'm calling W. Okay, is this clear so far? What I meant by W?
Yeah.
Yeah. Now I sort of I can say everything algebraically, but I want you to sort of see it geometrically. So this was the point x0, and there was this W, and consider solutions of the form. What did I do? So, x0 plus t times W, where t, imagine t is being changed from 0 slowly to some large positive number and slowly to some large negative number. And when you do that, geometrically what you're doing is you're moving along this line either in this direction or this direction. Okay. So now that means you had your initial solution. This was your x, and to that you are adding t times W. Now but W has non-zeros only in the same coordinates as x. If wherever it has non-zero coordinate values, x also has non-zero. Now, as you increase your t, those non-zero coordinates of x0 might change. Okay, wherever there is non-zero. But go ahead. No.
Yeah.
That's fine. So if as t increases, or maybe the general solution starts looking like x0. Let me write. So the general solution starts looking like x0's first coordinate plus t times w's first coordinate, and so on. Okay. Now, if all these coefficients w1, w2, and so on are non-negative, then we can go indefinitely in this direction w and stay within the feasible range. But if that was the case, then if you move in the opposite direction, we are going to use negative values for t. And then at some point, some variable will start complaining that you are forcing me in the negative direction, and we stop at that point, at that boundary. Okay. So then what has happened? We have got a new solution, namely this with that t star for t, where this variable, which was earlier non-negative, strictly positive in x0, has now become 0. No new variables, which were 0 initially, have been turned into non-zero. Yeah. So we are safe. Yeah.
Yeah. Okay.
Sorry, how do you know no variable has been turned to 0?
Yeah, because we defined our k carefully, where everybody had initially strictly positive values.
Okay.
Yeah. If some of them already had positive 0 values, then we would probably be completely immobilized. We will be able to move neither left nor right. We know that we have wiggle room. Yeah.
So you are only moving in the axis of those variables which are not strictly set to 0, right?
Say that again.
I mean, you are only moving along the axis of those variables which are not set to 0 yet, right?
I am moving in a direction where the only variables being changed are the variables which were strictly positive.
Non-zero. Yes, thank you.
Yeah. Which were non-zero, hence strictly positive. Yeah, but I'm not necessarily moving in a coordinate direction. I'm moving in the direction W. And I need to do that because I need to make sure that these equations stay satisfied. I ensure that these equations stay satisfied by this. Yeah, question. Yeah, Shubhadra.
So this gave us another feasible solution.
Yes.
So now what? I mean,
now what?
Still we have to prove that.
So now what? So there are two ways of doing such arguments. What I'm saying is some sort of an induction argument. One thing is, you could say, consider the feasible solution, which gives the objective value, which is at least this, which has the greatest number of zeros. Okay. And we argue that if the columns corresponding to it, the positive columns corresponding to it were not linearly independent, then we get a contradiction. And we stop there and say it must be the case that the columns were linearly independent, and you can then extend it to a feasible set.
Sorry, question. So
Yeah.
how did we say that this new solution is its objective values at least as much as that with X?
I decree among all solutions. So it's not, I don't prove it. I say among all feasible solutions, we know that there is one which achieves this much. Okay. Restrict yourself only to those feasible solutions. I did not, I think, say it the first time. So probably that's what is misleading you. I'm saying it now. Look at all feasible solutions which achieve at least this much. And among them, look for one which has the largest number of zeros in its solution.
Okay.
Okay. Now, let that be your X naught. And and perform this argument. In that solution, look at the places where you have non-zeros. My claim this time is that those places must be linearly independent. If they were not linearly independent, I could do this maneuver and find another solution whose objective, so one second. So in this, I of course missed one important thing. When you move in this direction W, okay, and if in this direction you can go on indefinitely, and in this direction, W's was giving you, thank you. I think you pointed out something. So one has to be careful in which direction one has to move. Okay. So
so only one of the directions will increase the objective value, right?
No. So let's see. So if that direction happened to, so in W, it could be that both directions are completely orthogonal to the C. Okay. In which case we could move in either direction and nothing is going to happen to the objective function, and then we are safe. Or it could be that in one of the directions, as we move, the objective function increases. Then in the opposite direction, the objective function will decrease. Okay, so suppose it was the case that we could move in either direction in W and nothing would happen to the objective function, then the old argument still works. Okay, but suppose it was the case that in this direction, C transpose times W is strictly greater than 0. Okay, in the positive direction of W. And you could go on indefinitely in this direction without violating feasibility, then the linear program was unbounded, because by moving in the direction W, you could have gone on forever. So we can assume that the direction in which we can move to increase the objective function is the direction which hits the wall at some point. At some point, some variable would have become negative. So we go in that direction. So as we are traveling in this direction, we know that the objective function is only improving, and we reach a point where we have an extra 0 in our solution. So is it clear, or should I say the whole thing again?
So sorry, if we're at the boundary,
yes,
and the direction along the W where you have to go to increase the objective value takes you outside the feasible set, then what do you do?
Sorry?
So for example, if you're at a boundary but not at a point, for example, this line segment here.
Yes.
And the direction
suppose
along the direction along
W will have to be then on the boundary. Because W, the direction of W always maintains feasibility. W cannot take you, traveling on W in either direction keeps you feasible as far as these equations are concerned.
Okay.
So maybe, so let me say that again. So maybe I should draw. So here, Shrishja's situation is, suppose the point was here. Okay. And we do the same thing and we get a W. Then that W should be a W, so that whether we add T times W or subtract T times W to the current position, it continues to be feasible. So W will be something like this. Now it can be that your objective function was pointing in this direction, then this W actually reduces the objective function. So we work with the negative of that W. Okay, when we work with the negative of that W, we ask, is there a point at which we become infeasible for this reason? If we don't, then the linear program was unbounded because we could travel in W indefinitely, yeah, without it becoming infeasible, and that will boost the objective function arbitrarily. So it must be the case that there is a time at which we become infeasible, and that must be because some variable here is becoming negative. So we stop there and we get our contradiction. If you want to think about it in contradiction language, or you can think of it as an algorithm which repeatedly keeps adding one more zero to the current solution. Is that okay? Sorry, I mean,
Yeah.
if you please read the book, it does that compact solution argument using this notion of the solution which has the maximum number of zeros. But I mean, since we are computer scientists, it might help you to say, well, if somebody gave you a solution, you can always perturb it and slowly in a few steps reach a solution which will be a basic feasible solution. Okay. So I didn't say it very well, but please read the book, and it is all said very nicely. But the idea is this, yeah, if you have linearly dependent columns, you can find a point in the null space, and that null space allows you to navigate either to this boundary or that boundary. And if you never hit a boundary in some favorable direction, then the linear program must have been unbounded to begin with. Okay, so now, if you have a linear program which is feasible and
I have one question, sir.
Yeah, please go ahead.
Is there any way to check whether it will be unbounded or not without like doing the computations? Like, I mean.
So given a linear program, whether it is unbounded or not, there is no easy way. You have to, so you have to do some algorithm anyway. Yeah, it's not immediately obvious that there is no simple way of telling whether the linear program is unbounded. Okay, but I'm just So I think I'm going to sort of ask you the question back in 5 minutes. Just wait. Let us do this corollary and then we will talk about it. Okay. So suppose you have a feasible linear program and it is bounded. Okay, all in equational form. Yeah. Then it has an optimal solution. So it is bounded, but there may be no optimum at all. Yeah, it takes smaller and smaller values. This does not happen for linear programs. And why?
Compact set.
No, so we don't want to say that some space is closed, etc. Even here, things can be unbounded. So the feasible region can be bounded. Only the LP is bounded. By LP is bounded, meaning there is an upper bound on the objective function in the entire feasible region. It's not saying that the feasible region is bounded. Okay, yeah. But what do we know? That whenever there is a feasible solution, there is a basic feasible solution which does at least as well. Is that okay? That's what we proved. If there is a feasible solution, then there is a basic feasible solution which does as well. Okay, so what can we do? Now we don't need your compactness or closeness. What can we say?
At most n choose m basic points.
That's right. So for every feasible solution, there is a basic feasible solution which takes value, objective value, which is as good as that of the feasible solution. So now restrict yourself to basic feasible solutions. And if the function is bounded, then one of the basic feasible solutions must be achieving the optimum. Okay. But there are finitely many basic feasible solutions, because basic feasible solutions are determined by the matrix, by the M cross M matrix. Okay, so if you go over among the basic feasible solutions, find the one which achieves the maximum. The claim is that that is the optimum. Why? Because this is bigger than or greater than or equal to every basic feasible solution. Take any other feasible solution, it is already being dominated by a basic feasible solution. So this special basic feasible solution must dominate all feasible solutions. So it must be the optimum. Okay. So optimum always exists. And in fact, it is achieved at a basic feasible solution. But so if the LP is bounded, then there is a basic feasible solution. So in principle, at least, I mean, we know much more, but this problem is computable. That is, when you are given LP in equational form, in principle, you could try each of the n choose m square submatrices there. Okay, solve it using Gaussian elimination. If the solution turns out to be feasible, that is, all the variables came out to be non-negative, it is a potential basic feasible solution. Compute the objective value. Try the next basis. Try the next basis. Systematically go through all the n choose m bases and find out which one gave the maximum value. And if your LP was bounded, then one of these will be the optimum. So this is an algorithm. It takes very long, perhaps, because it depends on how many equations you have and how many variables you have, because it's n choose n. Yeah, but at least in principle, this is an algorithm. But this algorithm is strictly not correct when the LP is not bounded. That is, yeah, there is no optimum. And the reason there is no optimum is that there are arbitrarily large values that the objective function can take within the feasible region. Okay, so this algorithm will not work. So the book asks you as an exercise, how will you modify this method? Okay, so what is the method? Go through every square matrix, square submatrix, m cross m square submatrix of your matrix, and ask and solve it using Gaussian elimination and check whether it's a feasible solution. If it is, then record its objective value, go through all of them and find the best. Now, it may be that even though the original LP was unbounded, this method, since it went through these basic feasible solutions, it came up with some number, 76. But actually, it is an unbounded LP. So what should you do? How will you modify this algorithm, which comes back to the question that was asked? How will you modify this algorithm? Yeah, you can still be inefficient. No problem with being inefficient. How will you modify this algorithm so that you will also be able to detect that the LP is unbounded? So this is an inefficient way of detecting whether the LP is unbounded. But as far as the exercise is concerned, that is enough. Okay.
So let M be the maximum of all the basic points.
Yes.
And add another constraint that inner product C, X strictly greater than M. If this is feasible, then it means the LP is. So let M be the maximum objective point of any of these basic points.
Yes.
Now add another constraint to the LP that inner product C, X is greater than M.
Yes.
And if this is
so it is strictly greater than M. Yeah.
And if this is feasible.
Yeah. So the thing is, you are pretty close. The strict inequalities, are not allowed in our LPs. LPs always we write greater than equal to. Okay. So yeah, so you can modify your answer slightly to deal with the situation. Yeah. Okay. So we are not allowed strict inequalities anywhere in our LP. That is why things are closed, and that is why this thing holds.
Actually, anything greater than equal to anything larger than M, M plus epsilon greater than equal to M plus epsilon will also work.
Yeah.
Because if there is a solution that is greater than M, then there is an unbounded solution.
Yeah. So you find a value, and then
and
you
then
ask.
If there
you
is
increase it by a little bit and ask whether there is a solution even
C,
for that.
X greater than equals to M plus 1.
Yeah, that is correct. Yeah, that will work. All right. So that's all I wanted to say about the equational form. Yeah. And so I just now want to make some remarks about convexity and relate it to the feasible region of LPs in equational form. Okay. So when do we say that a set is convex? I'm sorry, I mean, I'm probably saying things that you learned in high school or many years ago, but the book develops everything slowly, and there is there is some virtue in reviewing things that we already know. Okay, so you have a subset of R to the power n, and we are asking whether it is convex. Yeah, so what do we mean by convex? That whenever there are 2 points, yeah, in X, then the entire line segment joining the 2 points must be in X. That's correct. So whenever a set satisfies this property, it is called a convex set. Okay, so yeah. So here it may be that there are these 2 points, and if you look at the line joining them, it sort of leaves this set. So this set is not convex, and I hope somehow this set is convex. Okay, so you understand. Yeah. Now, the convex hull of a set of points S, yeah, a convex hull of a set of points S is, so there are 2 ways of defining it. We will look at both of them. So a convex hull of a set of points is the smallest convex set which contains these points. Okay. Now, it's often a useful definition for proving things, but for visualizing, it's not such a great definition. But nevertheless, what do we mean by that? Look at all convex sets that contain this set S and take their intersection. So those points which belong to all the convex sets that contain S, that will itself be a convex set. Yeah, because if 2 points are in this intersection, then both those points exist in each of those convex sets. Hence, the entire line segment joining them existed in each of those original convex sets whose intersection you took. Okay, so this will be a convex set, and since it is there in every convex set, this must be the smallest convex set. So there is a notion of a smallest convex set, and that is called the convex hull of this set S. Okay. The other way of defining the convex hull goes through what is called convex combination. So you are used to linear combination already. We put one more restriction in linear combination. So you have some k points. A convex combination of these k points is a linear combination where the coefficients have to satisfy a certain restriction. First of all, the coefficients should be all non-negative. Yeah, we can, yeah. And they must add up to 1. Okay. So it is an average of these points. So you take the average of any set of points, that is called a convex combination. In the average, you can assign different weightages to the different points. So that is called a convex combination of the points x1, x2, and x3. Now you've been given this set S. So what you do is that, sorry, what did I do? It's all messed up. So this should have been, sorry, this was okay. I don't know why I did that. Yeah. So let's see. So you've been given a set X, which is a subset of n-dimensional real space. What you do is you take every possible convex combination of some finite set of points in X and collect them together. Okay. So maybe you had some points here, and you take any point that can be obtained as a convex hull, as a convex combination of some other points, and you put them together. What you will be left with in the end will be an object like this, and the claim is that this is the convex hull. So this is more like algorithmic. Of course, you are doing infinitely many steps here, so I don't know why this somehow makes us feel better. But yeah, so you take the set of points X and take every possible convex combination of these points, of any finite set of these points, and the claim is that that is indeed the same thing as the convex hull. Yeah, the convex hull, which has been defined in terms of the smallest convex set, is the same as the set of convex combinations that you can obtain in this way. Okay, and again, how do you prove this? You show that this set is already convex. Yeah, let you do that, and that this set is contained in any convex set that contains X. Okay, and again, it's not very hard to see. So this is another way of thinking about convex hulls. Okay, good. So a hyperplane, you know, is defined by a set of by an equation of this kind, where this quantity is non-zero. Yeah. And what we mean by a closed half space is that whenever you have a hyperplane, one side of the hyperplane, where instead of equality here, this inequality holds. Okay. So yeah, this is called the closed half space. So the hyperplane itself is included in this half space, and also everything to one side. Okay. And a convex polyhedron, yeah, a convex polyhedron is an intersection of a finite number of closed half spaces. So you take one half space like this, another half space like this, and another half space like this, and then the final space that you get, yeah, that is called a polyhedron. Okay. So, and if the polyhedron happens to be bounded, so this is a convex polyhedron, and if it goes off to infinity in some direction, then it's not bounded. But if it is bounded, that is, there is a big ball inside which it can be placed, then it is called a convex polyhedron. So once again, what all did we say? We said a hyperplane, which you knew, half space, which you probably immediately were able to imagine. A polyhedron. Polyhedron is just intersection of closed half spaces, but a finite number of them. Okay, and there is no restriction that this polyhedron should be bounded. It can go off to infinity, like some conical shape like that. Yeah, that's also a polyhedron if the faces are all planes, planar faces in 3 dimensions. And if it is bounded, then it is called a convex polyhedron. Okay. Now, what is the dimension of a convex polyhedron? So it could be that, for example, you are in 3 dimensions and you have this hyperplane, and you consider the half space which is to one side of the hyperplane, and you consider the half space which is to the other side of the hyperplane. Okay. And you take the intersection of these 2 closed half spaces. Then you are left with just this hyperplane. And now you intersect with some other hyperplanes. So in the end, even though you are in the ambient 3-dimensional space, what you will be left with will be a thin figure, yeah, which is restricted to this hyperplane, because the first 2 half spaces already put you in this 2-dimensional space. Okay. And then when you intersected, you might have got a little pentagonal shape inside this plane. Then we say that the dimension of this polyhedron, yeah, is 2, even though you are sitting in a 3-dimensional space. Okay. Yeah. And maybe in the end, there were some more intersections, and all you were left with was a line inside this plane. Okay. In which case, we will say that the dimension of that polyhedron is 1. So what is the dimension of a polyhedron? Okay. You might be a polyhedron in R to the power n in the n-dimensional space, But consider the smallest affine space that contains, or the dimension of the smallest dimension of an affine space that contains your polyhedron. That is called the dimension of the polyhedron. So is that clear? Yeah. So any questions up till now? Yeah. So there are standard examples of polytopes. For example, the cube, which you know. Yeah. So you take the convex hull of those 8 points. Yeah. So which 8 points? Or in 3 dimension. In general, there are these 2 to the n points. Yeah. +1 -1 to the power n, and you take the convex hull of these, that will give you a polytope, yeah, with 2 to the n vertices, yeah, and that is called the hypercube or a cube. Okay, the cross polytope is essentially is Shanton's diamond. So you take all these basis, what are they called? The standard basis vectors, EI minus EI, okay, and you take the convex hull of them, yeah. So you get this pyramidal shape. So that is called the cross polytope. So yeah, and then the simplex, the standard simplex is you just, instead of taking EI and minus EI both, you just take EI, E1, E2, E3, the 3 standard basis vectors, and you take the convex combination of them, and what you get is a simplex. Okay. So again, this has been defined by taking convex combinations of set of vertices. Okay. Good. So these are examples to keep in mind, just terminology, nothing has happened. Okay. So far, we have done 2 things. We talked about linear programs in equational form, and that was one discussion. Then I moved to convexity and told you some things which you probably already knew. And now, in the last part, 5 minutes, 10 minutes, I would like to somehow connect what we did in the first part and these notions that we studied in convexity. Okay. So suppose P is a polyhedron, yeah, and we say that a point of an element of this polyhedron is a vertex if it is the unique optimum of some linear objective function. So, okay, so if there is a non-zero vector C such that C transpose V dominates C transpose Y for every point other than V in the polytope. Okay. So, yeah, so if a vertex of a polytope or a vertex even for a convex set, yeah, is an object like this, yeah, so you have, and suppose you have an objective function like, this is going to mess me up, like this, then if you look at the hyperplane, which is perpendicular to this direction, it meets it at this point, and that is the unique optimum. So it has to be the unique optimum. So if, so by a vertex, we mean a point which is the unique optimum of some objective function. Okay, that means there is a hyperplane where the polytope is entirely to one side, or polyhedron is entirely to one side, and the only point of intersection between that hyperplane and the polyhedron is the vertex V. then that vertex V is called a, sorry, that point V is called a vertex. Okay, let me say that again. So yeah, if find a hyperplane which has the polyhedron to entirely to one side, and the polyhedron and this hyperplane have only one point in common. Once you have found this, that point which is in common will be called a vertex of the polyhedron. Okay, so this is a definition. Okay, so that's what I've tried to say. So if you look at this hyperplane, yeah, so you, where those points which have the same objective value as the objective value of the special point V, P lies entirely to one side, and of course it intersects only at this vertex. Okay, yeah. So what's that? Okay. Any questions so far? Yeah. So the claim is that, so if you have the set of all feasible solutions of a linear program in equational form, then V is a vertex of P if and only if V is a basic feasible solution of the LP. So this is the connection between the first part of our discussion, which was very algebraic, defined by square matrices and all that, and the second part where we are thinking geometrically and imagining that there are points where some objective function takes the value, optimum value. Okay, so now, the set of feasible solutions of a linear program in equational form, you can check, is always a convex set, and it has been defined by intersection of closed finite number of closed half spaces. So it's a convex polyhedron. Okay. So yeah, so how do we prove this? So V is a vertex of P. Yeah. So what does that mean? Yeah, so that means there is an objective function which takes the best optimum value at V, but we know that so there is always a basic feasible solution which takes the same value as V. So it must be that V itself must be basic. Okay. And the other direction is that suppose we are given a basic feasible solution. Okay, so I'm claiming that this direction, that if V is a vertex, that very vertex will be a basic feasible solution. Okay, this is the easy, which is because of some other things that we had already proved. That is, the optimum occurs, or for every feasible solution, there is another feasible solution which achieves a value, which a basic feasible solution which achieves as good a value, and that already implies that this V must already be a basic feasible solution. Now, the other direction is when you have the algebraic definition gave us a basic feasible solution. So you looked at the linear program in equational form, and you found a particular basis B, and there was a basic feasible solution corresponding to that B. Now, why should that particular point actually be a vertex of the corresponding polyhedron? Okay. So what do we need to do? We have to cook up an objective function which takes its unique optimum value at that point. So what do we do? Well, so let me write. So here was your matrix A, and in that there was this matrix B, and the current point V happens to be a basic feasible solution. That means its non-negative values are all confined to these coordinates. Yeah. Positive value. Okay. Go ahead.
So let's consider the all ones vector on its zero coordinate and say minimize inner product with this vector in the universe.
Yeah. So consider the C, which has ones just outside and 0. So consider the C, which has ones outside of this basis and 0 in this basis. Yeah. So with 0 in these coordinates corresponding to the basis B. Yeah. The claim is that so any solution. So this particular vertex V. Yeah. So is it clear what C I meant? Yeah. So consider the C. Let me write here. So C is what Srijato just said. Put ones outside, 0 in B, and something like that. Yeah. So in the coordinates corresponding to B, you put 0. And we put -1 or +1. What do we want? We want maximum or minimum? Maximum.
And the minimum.
Sorry. Yeah. So I have been writing everything in maximum. So should I put -1?
-1.
Yeah. Put -1. Okay. Consider this C. Yeah. Consider this C. What is the value that V provides for this objective function? Well, if you take the dot product of V with this vector, V's non-zero coordinates are all here. Yeah, in this part. So V is going to give the objective value 0. Now, if any other vector gives objective value 0, then it must have zeros in these coordinates. That means it should also be a basic feasible solution with the same basis, because it has zeros elsewhere and it is a feasible solution. But we know that once you have fixed a basis, there is a unique basic feasible solution. So that solution must also have been V itself. Okay. So there cannot be a feasible solution different from V, which gives an objective value 0. So what did we achieve? We started with a basic feasible solution B, and using this objective function, which puts negative values outside of B, we concluded that for this objective function, V is the only optimal solution, and the objective value actually is 0 for V. Okay, so that's the connection between vertices and basic feasible solutions for things in equational form. Now, one has to be a little careful. So, yeah, this is the main part for our discussion, because the next, on Thursday, we'll be talking about the simplex method, and we'll be working with the equational method. But basic feasible solutions are also considered for arbitrary system of arbitrary linear programs. So what do we mean when we have a linear program like this, yeah, where we are allowing ourselves inequality constraints as well as equality constraints, and any constraints on variables are already being included in this statement here. Yeah. So what do we mean? So there is a definition of basic feasible solutions for general linear programs, which are written in this form. And the definition is that for a linear program like this, we say that a feasible solution is a basic feasible solution if, so now instead of columns, we move to rows. Yeah. So there are some n rows which are satisfied with equality. Okay. So whenever there are some n rows which are satisfied with equality, then we say that it is a basic feasible solution. Yeah. So now this sort of makes it appear that there are two definitions of basic feasible solution, one for general linear program and one for equational linear program, but equational linear programs are also general linear programs. So it looks like for equational linear programs, there are two solutions of basic feasible solution, two definitions of basic feasible solution. One, when you think in terms of these columns being linearly independent, and the other is where there are some equations which are holding with equality. Yeah. So the point is that if you have a basic feasible solution according to our original definition here, yeah. So there was this matrix B here. In the new setup, these equations, these inequalities will also be written as some, minus x1 less than or equal to 0, minus x2 less than or equal to 0, and so on. Then what you can do is you take this basic feasible solution and together with this part, yeah, and you will see that these equations have been satisfied with equality, and also these equations have been satisfied with equality. So there were m equations that were satisfied with equality already by this, and in addition there were some remaining variables, n minus m of them, which are satisfied, which are at 0. So those equations have been satisfied with equality. So if you have any basic feasible solution according to this definition, you can add to them these equations outside of these. Yeah. And you can imagine that that is a basic feasible solution according to this definition. And similarly, if you have a basic feasible solution here, the point is that there are only m equations here, so there must be n minus m variables here which are at 0, yeah, or n minus m of those equations must be from here, and yeah, and then you can go back and say that the same solution is actually a basic feasible solution according to this definition. Just a minor point: don't be alarmed that we have two different definitions. They actually lead to the same notion of basic feasibility when the system, when the linear program is presented in equational form. Okay, and maybe I'll take a minute and go over some points. The trouble with general linear programs, and why we are trying to avoid them somehow in our simplex method, is that sometimes you can have general linear program where you have an optimal solution. Yeah, it's not an unbounded LP. It's a general linear program which is bounded, but it has no basic feasible solutions which are optimal. Okay. Yeah. So imagine, for example, two hyperplanes which meet like this, and we are looking at this cone generated by them. But the point is that it's not a pointed cone. It is like a book, open book. Yeah. And suppose your objective function is somehow perpendicular to what is this called? The spine of the book. Then every point on the spine of the book is actually an optimal solution. But actually there is no basic feasible optimal solution. Okay. So such pathological things can happen in general linear programs. But in equational form, if there is an optimum, then there will be a basic feasible optimum. Okay, and that somehow makes things pleasant when we try to do the simplex method, which we'll do on Friday. Now, for general convex sets, vertices can be defined in two ways. Okay, or rather, there are two kinds of points which are important. One is a vertex. Okay, so what do we say? A vertex is a point where some linear function achieves its unique maximum. I'm just talking about a general convex set. A general convex set, a vertex is a point where some objective function, linear objective function, achieves its unique maximum. Okay. So that is what is called a vertex. And there is something called an extreme point. A point is called extreme if it cannot be written as a convex combination of two other points. Okay. Now it turns out that for convex polyhedra, vertex and extreme points are the same. But this is not the case for general convex sets. So so I let you think about this. So if you have a general convex set, it is not the case that at every extreme point that you can find a hyperplane which touches the convex set only at that point. Okay. So, but it turns out that for convex polyhedra, at least, notion of a vertex and extreme point are the same. And then there's one last thing. If you have a polytope, then we know that it's a polyhedron, so its vertices and extreme points are the same. Then every point of the polytope can be written as a convex combination of its vertices. So a polytope can be defined in two ways. You can say it's a bounded polyhedron, that is, it's an intersection of half spaces, or you can say that it is the convex hull of its vertices. Okay. Now, one direction is easy. If you have vertices, then every convex combination of those vertices will definitely be contained in the polytope. No problem about that. But every point of the polytope can be written as a convex combination of its vertices. Is some slightly non-obvious theorem. We will not discuss it now. Okay. If later on we need it, we will talk about it. Okay. Yeah. So that is all I wanted to say today. Yeah. So I told you about linear programs in equational forms and basic feasible solution, and the relationship between basic feasible solutions and vertices of the polyhedra that arise out of linear programs in equational form. Okay. If there are any questions, I'll answer. Otherwise, we can leave. Questions? All right. If anybody wants to add anything, stop. Yes, Sunandan, you wanted to say something?
No.
Okay. Okay. So we'll stop. Yeah. Thank you very much. I went over time. I'm sorry. Okay, we'll meet on Thursday. Okay. Bye. Bye, Kavita. Bye, everybody.
Bye.
Thank you, sir. Bye.
Bye. Thanks.
Bye.